Hey, what's up? It's Jake from Nimbus DevOps, and we are finally at the end of talking about generators. I'm sure you're sick of it by now, but if you're really looking for a deep dive on generators, you've come to the right place. So let's look at how generators behave in built-ins. So generator-like behavior is quite common among built-in types and functions. There's a major difference between Python 2 and Python 3 because in Python 2, functions like map, zip, filter return lists instead of iterable objects. The idea behind the change in Python 3 is that if you need to make a list from those results, you can always wrap a call in the list class. And then you're done. And we've done that. We've produced a result, returned a value, whatever, and then just said, hey, list whatever that return value is. And then it just converts it to a list, which is super handy. If you need to iterate and want to keep the impact on memory as light as possible, you can use those functions pretty safely. Another notable example is in the range function in Python 2, it returned a list, and there was another function called xrange that behaved like range, which now behaves like that in Python 3. Just little differences. I don't expect anybody here to really ever use Python 2. Um, but you might see it maybe. I've never really seen it in the wild, not in a very long time. A lot of people just moved on to Python 3. The idea of functions and methods that return iterable objects is quite widespread, though. You can find it in the open function, which is used to operate on file objects, which we're going to do a lot of when we start looking at data persistence and how to take this code that you're learning and use it to manipulate files and create files and do all these other things. Which will be the fun stuff, right? But you can also enumerate in like dictionary keys, values, items, methods, and other places like that. It makes sense though, like, right? Python's trying to reduce the memory footprint and avoid wasting space if possible, especially in functions that are used extensively, like open or enumerate. Um, so earlier, many videos ago, I said that it makes more sense to optimize the performance of code that has to deal with a lot of objects rather than shaving off a few milliseconds from a function that you can call twice a day. And that's exactly what Python's doing, like inside of itself. So, one last little example before we finish up. I'll show you a problem used to submit to Python people in a developer role. The problem is to write a function that returns a Fibonacci sequence up to some limit n. We've talked about Fibonacci many times, but it's an excellent sequence for testing knowledge about recursion, memoization techniques, and other technical details. But in this case, it's a good opportunity just to check whether or not you know about generators. And so this may be something you'd see in like a whiteboard interview or a coding interview or something like that. And so we're just going to take a look at how we might do this. And made a file called built-in because that's why I started calling this, but we're going to make some Fibonacci stuff. So let's define a function called Fibonacci. Okay, it's going to take a number big N. And all we want to do, and I guess I can just put this in here as a comment, is return all Fibonacci numbers up to n. That's all we want to do. And remember to put a period so people know that your comments are complete and not missing something. And whatever the result is equals, we're going to make a result empty list 0, not empty list, but resist list 0. So initializing that, right? And then we're going to say next underscore n. So the next number is 1. And then we'll say while next underscore n is less than or equal to big N. Okay, so as long as we haven't hit the limit, colon here, we're going to take result.append. So we're going to add to this list next, whatever next n is. And then we say next n equals the sum of results and then positioning -2 colon and then return the result. Okay. Oh, I didn't mean to do that. I meant underscore n. There we go. Sorry to make that confusing. Results. Let's see. Sum results This should be a square bracket. Okay, there we go. So now let's take that function and we're just going to print Fibonacci, and then let's try a couple different values. Let's do 0. We can print Fibonacci for 1, and then let's do some big number, which is going to make my computer very angry. Let's print Fibonacci for 50. Okay, so from the top, we set up a result list starting at value 0, right? Then we start the iteration from the next element, next n, which is 1. And while the next element is not greater than n, which is, whatever value we pass to it, we keep appending it to the list and calculating the next value in the sequence. And we calculate the next element by taking a slice of the last 2 elements in the result list and passing it to the sum function, which if you remember Fibonacci would be like 0, 1, and then 0 plus 1 is 1, and then 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8, and et cetera, and it just keeps appending the result list. So we add some print statements, and we should expect this to work just fine. So if I say Python built in, we see 0, 0, 1, 1, and then 0 through 34. And that works great. Great, you made a Fibonacci sequence. Okay, that's awesome. So when the condition of the while loop evaluates to false, we exit the loop, return the result. You can see it in the print statement that I did. And at this point, in an interview, or if you're just talking amongst your friends for fun, somebody might ask you, what if I just want to iterate over those numbers? And a good candidate would change the code to something like this. So let me comment this out and go, hey, I wanna define a function Fibonacci, but I'm gonna make a little bit different. I'm still gonna pass a big N, and I'm gonna do the same. I want the same exact result, right? But I just want to do it a little differently. I can yield 0, okay, and say if n not equals 0, then return. That's it. And then just say a equals 0, b equals 1, while b less than equal to big N, yield b, and then just say a comma b equals b comma a plus b. Then I can take these exact same print statements. I'll just copy them and paste them and then remove this comment. And we should get the same result. So let's print this and then talk about it. All right, so here's the built-in generator object. You can see that printing this gives you a position. So I have to wrap this in a list. Boom, boom. And then let's just say list and list. There. Same result. Very fast. So this is one result. So we can show you this. The Fibonacci function is a generator function. So first we yield 0, then if n is less or n is 0, we return. That'll cause a stop iteration exception to be raised. If that's not the case, you'll just start iterating, yielding b at every loop cycle, and then updating a and b. All we need to be able to produce the next element of the sequence is the past 2, a, b, respectively. So there's another version of this that is much lighter memory footprint, and all you have to do is get a list of Fibonacci numbers and wrap the call with list as usual. But what about like how elegant it is, right? So I wouldn't want to leave that like that. There's something better you could do. So if we define Fibonacci again, and we pass a big N, what if we just said A, B equals 0, 1, and then said, hey, while A less than equal big N, just yield A, and what are you doing? A, and then just say A comma B equals B, comma, and then A plus B, and then you have your last two. That is much better than this, right? The whole body of the function is 4 lines. I mean, 5 if you don't count if you put this in here. This is just 4 lines. In this case, the tuple assignment helps in making the code shorter and more readable. And this is pretty simple. So that's pretty much it. So in summary, we covered, we covered a lot. We covered iteration, generation, map zip filter, learning how to use them as an alternative approach to like a regular for loop, comprehensions for lists, dictionaries, and sets, exploring the syntax of um, classic for loops, and then the use of map zip filter functions, and then the concept of generator in the form of functions and expressions, saving time and space using generator techniques, not overdoing it, performance, all that stuff. Um, so yeah, that is a lot of information. So hopefully you got something out of this. It was a very, very long and difficult on the brain section. So hopefully that laid some foundation and gave you some options. And we'll move on to the next section, which is going to be kind of similar to this one. Different subjects, but it's going to get deep, y'all. So if you're just wanting to be a script kiddie, you can probably stop. If you want to tell people you know Python, you're probably good for up to this point. If you're continuing with me, I'm like halfway done, and it's just going to get even more and more and more and more difficult and complicated. But it's also going to get really cool. So um, hang in there. It's about this ride's about to get wild.